that, let me introduce Emilian Parau, who's going to talk to us about flexural gravity and capillary-gravity waves.
Okay, thank you, Dave. Just checking the title. So, yeah, thank you for inviting me for this meeting. And I should talk for 50-something minutes, 55 minutes about flexural and capillary-gravity waves. So I'm from University of East Anglia, and some of the research is sponsored by FSRC. The talk will be, again, mainly about flexural gravity waves. I'll make some comparisons with capillary gravity case, and I show the differences, some differences and some similarities. So there are two sort of, I'll talk about motivation and so on at the beginning. So I'll talk roughly in the first part about waves under an elastic plate or in finite depth, and then stratified flows under an elastic plate. And in the end, I have some few words about other related flexural or hydroelastic problems. I'm going to use the flexural gravity or hydroelastic more or less with the same sense in my mind. So if I say one, it's the same as the other. I have a list of collaborators, and some of them will speak today, later, Dan and Jean-Marc. Some of them will speak later in the week. And some will speak in Siam, like Charlotte. So the motivation. So the flexural gravity problems, as I said, there are some similarities between that one and the capillary gravity problems. The scales are very different. So on one hand, they have these sort of millimeter, centimeter waves, dead bitter and some sort of patterns of waves. I'm not talking about patterns of waves, but it's a nice picture. And here you have like a plane either taking off or arriving at a runway in Antarctica. And they generate waves in ice, which ice can be seen as an elastic plate under certain conditions. So again, the scales is like tens of meters, hundreds of meters, and so on. And people have measured waves under this sort of ice, and they're interested to see when they can use the ice as road or runways, so it's not breaking. And there are other uses of this sort of hydroelastic waves. You want to break the ice, sometimes you use air-cushioned vehicles. And another thing is that people have seen waves very far from the ice age. And again, we'll try to see how we can sort of describe these waves, how we can calculate them. And if you want to have some fun, you can see some killer whales making some waves, and they hunt seals which sit on some ice sheet, if you type the words. And again, because it's hydroelastic, so as I say, I'm thinking of ice, but it doesn't have to be ice. I'm thinking of an elastic plate. And there are some like Megafloat in Japan, some very large floating structures which are elastic in waves, and some floating islands if you read Jules Verne. There are a number of works on this sort of waves. There are some experiments with all these various depths in, as I say, it's mainly on ice on water, with the depth of the water varying from a few meters, like in Japan, to a few hundreds of meters, like the one you've seen when the plane was probably taking off. There are a lot of linear results, starting with Greenhill in 1886 and close to our days by Schulkes and some other people. And in the last 20, 30 years, some nonlinear results start to sort of be published. And it's not a complete list of people from here. The pictures I like to show most when I talk about this sort of waves is that one. So this is some experiments done by Takizawa. So he was having an ice skidoo traveling at constant speed, and he varies the speed, and then he measured the deflection of the ice on the lake with 7 meters depth. The lake, and I think the ice is 16 centimeters or 18. And then he looked at the profiles, and he see various sort of differences. You see the sort of like localized wave just under the load. You increase the speed, you see some sort of bridges appearing in this localized structure. And then you see waves in front or after the load and so on. So he measured carefully all these sort of deflections, and he put the depth of the deflection on a graph with speed, and he found there is this sort of interesting maximum, which actually corresponds to the minimum of the special relation. We'll see it later.
Question?
Yes?
What are the axes? Left, right?
I don't know. So meters.
On the right.
On this one,
Yeah.
is millimeters.
And what's
And this is meters per second, the speed, yeah?
And what's changing as you go down the,
I mean, so the depth, they're looking at this point under the load, the depth, how big is the depth? It is increasing and then decreasing if you look at this.
right? But what's the sequence of, something's changing as you walk?
Yes, yes, the speed, sorry, yeah.
Okay.
So this is a very low speed, and the speed increases and so on.
Thank you.
I think this one is working. Yes. So now, again, I look mostly of solitary waves, so I have no loads apart from in some cases. So this is the sketch of the problem. So it's very similar with the water waves. So we have some fluid and we have some elastic plate on top of it. I will talk mainly about steady waves. Zan will talk later about some unsteady waves, and Philip probably on Friday. You have the usual assumptions about the fluid, and so again, if you're talking about the ice sheet, there are various models, elastic models like linear models or nonlinear, or various type of viscoelastic models. In our talk, I'll talk about elastic models, and I'll show the derivation in a couple of slides. So let's not use this thing. So the formulation is very similar with the formulation for the water waves, or you look for velocity potential, you have kinematic condition and so on, you have Bernoulli equations on the free surface. The difference will be on this sort of pressure, which comes from the elastic model you're using. There are some things I'm neglecting here, for example, like inertia of the plate. Will bring you another term of rho eta tt or so on. And so that's elastic model. So I'm using this sort of theory of hyperelastic shells. I have a thin elastic plate and so on. You do a force balance on a small piece of this shell. On this graph, Q is the shear. Tau is the tangential stress. You have the classical vector n and t. If you do a proper balance of all these forces and moments, you'll find out some link between this tangential and the shear stress, and there's also some link between the shear stress and the moment, the bending moment. So you write these equations on the normal direction, on the tangential direction, and you obtain these three equations between tau, q, and m. You assume this link between the bending moment and the curvature, which is a standard assumption. And then if you integrate all these equations, you obtain these things for the pressure. If you remember, there's the pressure which will appear on this Bernoulli equation. So kappa is the curvature. The derivative is on R length. We do neglect the inertia of the thin elastic plate. And this sigma is a constant of integration, which again you can see it as a sort of measure of pre-stressing of the plate. We assume it to be 0 in our calculations. So it's so this is the last expression is the full expression for this for the pressure on Wallerian coordinates. So if I'm looking at the Bernoulli equation only, so the difference between flexural gravity and capillary gravity is this term. So this is for capillary gravity waves, so kappa is the curvature, and here is slightly more complicated one for the flexural gravity case. Again, there are some assumptions made, and sigma will be 0 later on. You do a analysis of linear waves, periodic linear waves, and you find the dispersion relation in the two cases. Again, the difference is this term. So this is for flexural gravity, this is for surface tension. And again, on the next page, you'll see the plots of this dispersion relation. So the main thing is for flexural gravity waves, you always have a minimum of the dispersion relation. If you are familiar with the capillary gravity wave problems, you may have a minimum if you have either large H or weak surface tension, depending on which are to fix. And you have the classical long wave limit C0, which is also critical speed. So again, if you look at what we've seen on the previous slide, so this is the dispersion relation C against K for flexural gravity waves, and this is C against K for the surface tension with different age. So for the flexural gravity, it doesn't matter the age, you'll always have this minimum. Here, if you're very small age, you have this sort of dashed line, which is a increasing function. Again, talking about the scales, this is the C in both graphs is in meter per second, and K is in 1/meters. So the flexural, I mean, this corresponds to Takitaba experiments. Again, 6 meters per second, the minimum speed, the C mean. Here it's 23 centimeters per second, roughly. And again, if you look at the wavelength, this is, I think, 15 meters, and this is like 1 point something centimeters, 1.5, 1.6.
You only get one minimum for the flexural?
Yes, you always have one minimum. Yeah. Well, it's quite about some tangent and so on. So now there's some, we can rewrite these things using what we've heard today and yesterday in various talks, but Hamiltonian formulation. So it's the method derived by Zakharov and later extended by Walter and Philippe and some other co-workers, I think. When you can rewrite the equations in a Hamiltonian form, and again, the difference is this term, which again, if you do capillary gravity waves, you have a similar stuff, T over rho square root of 1 plus eta squared minus 1. You can, from this formulation, you can use it to derive weakly nonlinear models, like the classical NLS when C is around C mean, and some KdV, which if you keep this sort of D terms, you'll have a 5th order KdV around C, around the long wave limits. I'm not talking too much about these things today, but you can do this sort of stuff. The big difference between capillary gravity waves and flexural gravity waves is that the NLS, it's focusing, so it does have this sort of solitary waves for all the depth for flexural gravity, for small depth for flexural gravity waves, but it's defocusing in deep water. So it means that the NLS do not predict small wave solutions in deep water for flexural gravity waves. So for NLS, for capillary gravity waves, as you know, as you've seen yesterday, Professor Akin's talk, you do obtain an NLS which is focusing at any depth. I'm concentrating more on the numerical computation, so we have the previous problems. You can find steady, you can find unsteady waves. Again, I'm talking about steady waves today because it's numerical workshop. I'll talk about more than numerical than usual. And so we're using 92, sorry. It's 1992, yeah? It's 10 years later. So the idea is for the steady waves, we use the boundary integral method, so it's different from what you've seen this morning. We do go on the inverse plane, which means that we expand x as a function of phi and psi, and y as a function of phi and psi. So we work on a fixed domain on the phi psi plane, when psi is the stream function. Then we discretize the potential and so on. I'll come a little bit later to more detail about these things when I talk about two layers, so that's why I'm not saying too much here. For the unsteady waves, again, some higher order spectral method, which is probably the type of things you've seen this morning. And again, you'll see more about this on the next talk and on Friday. So and the delicate anomaly operator you've seen before, you see that truncated and so on, and that's it's a method been developed in the past 10 years or so. So steady waves. What do I obtain with my boundary integral code? I do obtain these sort of structures, the so-called depression solitary waves, called like that because at 0 they have the amplitude less than 0. We do have also elevation solitary waves, which means that this middle of the wave is bigger than sort of the level at infinity. Now, if I plot the branches, so on this one you see these branches of depression starting from here, the black line, and going in this direction. And here is that one. The dashed one you can neglect for the moment. It's just a forced wave, which I use to obtain this sort of branch of solitary waves. So the interesting thing is that the critical speed, the corresponding to C mean, is 1.32 in our non-dimensional variables. And we do obtain that the branch of solution starts from some finite amplitude. For a related model, Zahn and Paul and Jean-Marc went beyond this C-mean, but with a different scheme, so they found this sort of generalized solitary waves. But in our case, we just stopped there, and so in capillary gravity waves, those branches start from the C-mean. In our case, start from some sort of finite amplitude. This is true in infinite depth. Now, another thing is that the elevation branch, it's have a very complicated form. So this is just the start of the thing. It just do various turns and so on. The depression is much simpler. You start from here, just go up to 0. So again, on capillary gravity, at some point you have to stop because it's various limiting profiles with enclosed bubbles. This one you can go up to 0 because at 0 there is a static profile corresponding to our solution. So if I put C0 in our solutions, in our equations, I can obtain some profile, and I see that my waves go to that profile, which is also overturning.
Can I just ask something?
Yeah.
Is it finite or infinite depth? Because at the top it says finite depth, at the bottom it says infinite depth.
Sorry, this is finite. This is infinite depth.
This is infinite
Yes,
depth.
yes.
Okay.
Now it's finite. my choice of words, maybe not. But so this is true for infinite depth. So now what happens with this branch? So I'll show some limiting profiles later. So what happens with this branch when I have some finite depth? So the numerical method is not very complicated to change it. Just put some bottom and do some slightly different Cauchy integral trick. So what happened with this branch? So that this branch of depression solitary waves moves. So this is the solid one is close to the infinite, which is 8. After that, it doesn't change too much, and it moves upwards. So that the amplitude of the waves decay when the depth of the water is decreasing. And at some point, like this, in this case, when it's quite shallow water, the upper one, they start from the critical point, from C-mean again. So they start from somewhere finite here, and then they start exactly from the critical speed when you go. But the critical speed obviously depends on h, so it just changes with each branch. And if you remember the NLS on shallow water, it is focusing, so it should sort of start from there. And now going to the other side of what happens at the end of the curve. So that's what you obtain. So you have this sort of overturning profile, start to overturn the waves. And then if you continue up to c equals 0, you do obtain this sort of self-intersecting profile. So this is the sort of profile that you can compute with a different code, just using Runge, Kuta, and so on, because you have just kappa as an unknown. So our branch goes from the C-mean from finite amplitude up to the c equals 0, and you obtain this sort of profile, which is slightly unphysical, because this is an elastic plate self-intersecting. So, okay, talking about physical stuff, maybe I'll talk a bit later. So, if you think of ice, you have to be careful about the strain in ice. So, at some point, the ice behaves break. So, there's sort of field strain of ice. So, if you have to compute the strain in all these solutions and see when they're sort of beyond the critical thing. I'm sure that those ones are beyond the critical thing. So, there's not maybe true for the ice to see these solutions in ice. Now, if I plot this, the energy or the Hamiltonian energy I had before, so what's an interesting thing, so it's the same graph on the left and the right, but this is closer to the C-mean. This is again, I think, infinite depth. I show it, yes, infinite depth. So the depression, the energy for the depression branch is the solid one. The dashed one is for the elevation branch. And this is the same depression one, but from 0 to up to here. So you can see there is a minimum of this sort of energy. And then you have another maximum. And Philippe and I will look to see what happens when you have waves in various regimes. And it seems to be that on this sort of region, the waves are unsteady. So if you put the solutions, they'll sort of not break. They just have all the dispersion. And while if you're here on this sort of area, you find the nice solitary waves moving as much as you want on the almost on the unsteady code. So. Okay, so this is the sort of part with the finite depth. Now the thing is, because under the water, if you think about the ice, just under the ice, there's a water which is, I don't know, less salty than far below. So you may find sometimes there's some stratification under the ice. So what happens if I consider now the effect of the stratification and the elastic plate? And if you want some sort of motivation, it's various observation of ice. They've seen that the wavelength of the ice cannot be explained by the flexural effect because they're much longer. And they say that they're probably interpretation of the internal waves signature on the elastic plate. So this is just to give an idea. It's somewhere in Canada, probably. Cambridge Bay. I don't know. I'm not very familiar.
It's very close to Cambridge.
Not this one. Yeah. So they measure the salinity in some bay, and this is the profile, this is the depth, this is the salinity, which kind of correspond again with, well, salinity, nothing else. So in particular, at the end of the spring, they found that, or sorry, at the beginning of the spring, you have this sort of constant layer with salinity here, and they have another constant layer of salinity there. So it's like a sort of two-layer fluid with some sort of transition between them. Now, obviously, for the moment, I'm just simplifying a little bit. So I have only two layers. So this transition is just this line, the eta of xt. So this is, again, a classical problem in gravity waves and in capillary gravity waves. So we have, obviously, another unknown, eta, which is the interface. We have zeta. You have two different densities. And you do the usual assumptions. Now we have two potentials to worry about, phi1 and phi2, in each of the layer. You have, again, plenty of kinematic conditions on the interface, free surface, and so on. And you have two Bernoulli equations. So this EB corresponds to this bending modulus, which is on some non-dimensional form here. So, and this is the classical Bernoulli condition of the interface. R roughly is the density ratio, and I don't think there's anything else you should know. F is the Froude number. Now, if you plot the dispersion relation in this case, you have two branches of the dispersion relation. It's a much more complicated form. I don't put it here. So if you remember previously, you have something like that, only this branch. Now you have another branch here. And you can use different names depending on the taste. So that one, it's the fast or barotropic or external mode. And the lower one is the slow or the baroclinic or internal. So I probably use slow or fast by default, but if you prefer something else, please feel free. Some analysis of this, especially, so this is again a generic case. There's some so it depends on some cases. So what can happen? You always have this minimum. Now people doing capillary gravity waves in two-layer flows, you do obtain sometimes the minimum, but sometimes you don't. Sometimes you have the dispersion relation going straight up from here, and this one going down. So again, capillary gravity waves, when capillary is only important at the surface. So I assume that at the interface there is no capillarity. So you always have one branch going to 0 and one going to infinity when cakes go large. And as I say, sometimes for capillary it just goes straight up. Well, in this case, it always go down, have a minimum, and then go up. The other one, we may have a maximum, a local maximum at a finite k, in some sort of unrealistic conditions, but again, interesting mathematically, I should say.
So this is the dispersion relation. The upper curve is for waves on the surface, and the lower one is for waves at the interface, or this is all for waves at the surface?
It's so you consider a wave which have the same, at the surface and the interface, the same sort of wavelength. And again, this is called whatever x. It's not purely surface. I mean, all those modes you see on both surfaces, some interaction between them. Roughly, we probably can say that the waves on the surface is determined by that one. But in what happens is there is an interaction between all those modes. So depending on whatever the value parameters, but you should see both of these things in both surfaces.
Emilian, if there is a maximum in the bottom dispersion relation, can it ever line up at the same frequency as the minimum in the top dispersion relation?
You mean this maximum here?
Yeah.
Very close. It can be very close. I mean, for example, I have in a related problems of internal waves with capillary only at the interface, but not at the free surface. You can put them on top of each other, basically, the maximum and the minimum. On this one, I don't think they can be exactly the same k. So that there is a k for minimum, another k for this maximum, as far as I remember. So okay, so let's see how do we compare with gravity waves. So again, the classical case of two-layer flows with free surface interface, nothing else, no capillary, no free whatever elastic plate. In this case, both these sort of you still have two modes. Both of them decay to 0 at infinity. So what sort of waves I can find on these cases? So in this case, I can find waves which have speed higher than this sort of fast mode, and this will be the classical elevation solitary waves you find for gravity waves. When you find waves around this critical mode, those one will have another sort of wave with a higher k traveling at the same speed, so we obtain the so-called generalized solitary waves. In a previous case, I'm a little bit lucky if I look for solitary waves. I can find waves starting from this minimum, as you do for what we've seen before, for the one layer. And then so I can find waves starting from this internal wave, because there is this gap in the spectrum between the minimum and the lower mode. And again, if you have a maximum here, I can have waves starting from this maximum, and we'll see the difference between the two. So I think I summarized what I want to say here. So again, coming to this one, so we have fast in-phase solitary waves like that. I think Moni and King have published one of the first paper on these things. So those are very similar with the normal elevation waves you see, like Russell, the solitary waves. And on the other waves starting from the other mode, you can see the so-called generalized solitary waves, which have a big pulse, and then there are small oscillations traveling at the same speed with a big pulse. Again, those waves are computed with slightly different programs. I'll come a little bit later on this one as well. We assume that the generalized solitary wave is a long periodic wave. Now, going back to the numerical method, I'll say I give some more details than I give usually for this sort of talks. So again, as for the waves in finite depth, I prefer to go in the inverse plane. So I expand x and y as a function of phi and psi. You have to remember there are two potentials, unfortunately, in the lower and the upper fluid, phi 1 and phi 2. There is a link between those potentials. People have done these things in the past. So Professor Akilas and Diaz and some other people have done these things in various other configurations. And the complication here is that, again, you have these unknowns at the free surface, which is given by a constant stream functions. So you have to find, roughly speaking, capital X, capital Y, which gives you the free surface, small x, small y, which gives you the interface, and that's the link between the potentials. So you apply the Cauchy integral formula in upper-lower fluid. You 3 times, you take whatever the point in the interface twice, and one of the free surface. You truncate, so the phi will be your independent variables, phi 1. And you want to find g, x, eta, x prime and y prime, when g is again the link between the potentials. X and eta will give you the interface, and capital X, capital Y will give you the free surface. And you have 2 Bernoulli equations for this and 3 Cauchy integrals. Now the trick is you can actually eliminate 2 of those things. So you actually need only 3n equations for 3n unknowns for eta, x, and capital X, capital Y. The other, you can use one of the Cauchy and one of the Bernoulli to find them after or before if you want. And then at the end, you obtain some nonlinear system. You use some sort of Newton method. And to kick off the things, you do the classical trick, the paper which was 10 years wrong. So you put some forcing, you follow the forcing, you jump on the solitary waves, and then remove the forcing and so on. And then after you remove the forcing, you just go by continuation, you just can walk around on the solitary wave branch. Yeah.
The truncation you do in phi 1, what does that correspond to back in the original coordinates? Is that a truncation in the vertical direction or the lateral?
On that one, yeah. On the infinity 40, I think so. And we have to check it obviously to see truncate far enough and so on. And then you just use discretize the points. In this case, we're talking about symmetric solitary waves. You'll see a little bit later Jean-Marc talking about non-symmetric solitary waves. So that's why I'm starting from 0 and so on, because I assume there's symmetric on 0. So in a couple of talks, you'll see something more interesting about non-symmetric ones for a slightly different problem. So what do we get? So again, I expect to see this sort of waves. Maybe I should draw a graph. So roughly, you have this sort of dispersion relation. So I expect to see waves from here, bifurcated from this sort of speed and from this wave number, and waves from here, the so-called fast and slow. So the fast one are here, and as you expect, they're in phase. So that's the sort of profile. This is the free surface. This is the interface. And then I can continue this one up to some limiting cases, limiting profiles. So the limiting profiles look quite nicely. So when the free surface, okay, the elastic plate almost touched the interface. So that's different limiting profiles for, if you remember what we've seen before. So in the case of one layer, you can go up to c equals 0 and define these overturned waves. Yeah, sorry, this is to my messenger. And in this, and again, in this case, you can go almost when the two surfaces touch. And those are for like realistic conditions when R is 0.9 or even higher. You can find elevation waves. So the previous one were depression ones. Now you can find elevation ones, as you do for the NLS, or in this case I shouldn't talk about NLS, but anyway, that's the idea. You find elevation and depression. And again, in this case, you can follow even, so the limiting case is when, again, those two branches almost touch. And in this case, the elevation sort of become depression. So the top of this wave is less than the 0 level. So this corresponds to this sort of, so the branches corresponds to these things on the eta f plane. So this is the critical point, the fast corresponds to the minimum, and then just carry on the branch. Now if I move here, I do obtain waves when the interface is of depression or the interface is of elevation, depending on age. And again, there's some study done on the gravity waves on two-layer flows, and there's discussion about age. So when H is the ratio of the upper to the lower, when you have a shallow upper layer and a deep lower layer, is this situation when you have an depression interfacial wave. When the other situation, it's elevation interfacial waves. And again, because there is sort of realistic condition on the free surface, you cannot see the effect, or it's much smaller the effect on the free surface than on the interface. But you do see the signature of these waves here, if you look carefully. And again, EB, it's sort of realistic. EB should be a little bit smaller for the experiments, but again, you cannot have this sort of condition in the experiments if you have a smaller water. So those waves, because they bifurcate from here, they're KdV type when they start. And the branch, so you can follow the branch of those solutions going up to some limiting configuration when they look like tabletop solutions, or here. And they start to broaden very fast at some given flow number. And this is the flow number corresponding to the conjugate flow number. So you can find some flows which have different depths in the one side and the other, and different speeds. And those things happen at some flow number, and this flow number is the one when our branch stops. So basically we're starting with our solutions from here, and we follow up to some sort of limiting stuff, and the limiting stuff corresponds to this sort of tabletop or table type solution. Now what happens if I change the situation from here, so I have a maximum at a finite, so it's like that. as you can see from this graph. Now the solutions bifurcates from this maximum, and because there's different type of solutions, it's not a KDV type of solutions, these sort of waves with oscillations, and now they're out of phase. Now I should mention that to obtain this minimum, to obtain this maximum, we do have to use some slightly unrealistic density ratios like 0.1 and so on. But again, mathematically, I think it's sort of interesting. What was interesting is that we couldn't find the waves of the other type on this case. All this gap is filled by this sort of branch, and this is at the moment when we arrive at this sort of minimum from here. So you follow the branch from here, go up, and then there is no space for elevation branch, for in-phase branch. Those are out of phase. Okay, now what happens? I mean, if you play the parameters, you can bring down this maximum much closer. So again, so in theory, you can have this sort of situation. So there is no gap between the waves, or the gap is very small. And in this case, you cannot find proper solitary waves between this internal type mode or slow mode, and they became generalized solitary waves. So again, a few words about generalized solitary waves. We approximate them with long periodic waves, and again, I'm working on the inverse plane. Now I just expand x, y, and so on on each layer as a Fourier series, and phi and psi and phi, sorry. And then because there is a difference in potential, I introduce an unknown function which corresponds to the g in the previous case, and then discretize. We have all these coefficients to solve. We have equations like Bernoulli equations, and I need to be sure that the x are the same at the same point on the free surface, on the interface. So you have plenty of equations and hopefully the same number of unknowns, and that's what you get. So now I moved from here there, so that this line corresponds to my front number for these solutions. So because I have two intersections with this branch, my solitary wave will have two different waves periodic with two different periods traveling on the tail. And you see from here that you have a sort of interaction of two different of waves with two different wavelengths. So apart from the main pulse, you have all these sort of small things traveling with you. And again, how do you know that those are generalized solitary waves? Well, you can put more periods, but just make the domain longer and so on, and nothing change on the solution. And with this code, actually, we can now go below this minimum, and all these things will disappear. So you just can go up or below this minimum without any sort of problem. So that's so you can play the parameters so that you have sort of various interactions here, like Wilton-Ripple type and so on. So and I'm talking about Wilton-Ripples on the tail only, not so that we have the main pulse, which is the main pulse, and so on. So obviously this is only half of the wave. The other half is just symmetric. And this is the free surface, or whatever, the elastic, and this is the interface. So that's roughly what happens in two-layer flows with flexural gravity. Now, as the title says, if you see on my slides, other related problems, we can compute other type of flexural gravity waves. So we've seen so far waves under an elastic plate, stratified waves under an elastic plate. We can do some three-dimensional stuff, or we can do waves like that. So there are some papers. So the configuration is you have a bump, and you can make solutions to have a fall on this one, a hydraulic fall. This is true for gravity case. This is true also for capillary gravity and flexural gravity case. And then you can trap waves between obstacles and so on. And if you want to know more about this, Charlotte will talk at the SIAM in 4 weeks' time about this sort of solutions. And in this case, the numerical algorithm is the other way around. It's phi as a function of x, not x as a function of phi. So it's sort of in a normal plane. Now, another sort of flexural gravity wave problem is a 3D one. So, so far we've seen only two-dimensional stuff. We can go to 3D, where currently trying to compute some waves with a full elastic term, but for the moment what I can show you is that one when I simplify a lot the elastic term. I'm actually using only a combination of linear elastic plane model and nonlinear flow, which you can probably defend it, but there's not a point here. So at the moment, as I say, we try to put the full nonlinear term here. We're still not there yet. And again, we use a bundle integral method, which is introduced by Forbes or maybe some other people. And we use a green second formula to get some phi relation between phi and zeta. We project these things on the plane, and then we have sort of rectangular grid to worry about. You take care of the singularities. Landweber and Macagno in '69, I think, for the first one. You take away some quantities, put them back, and so on. The classical trick to get rid of singularities. And then you end up with two NM equations, with two NM unknowns. It's the Bernoulli equation, the integral equations. And you do all sorts of tricks. So you integrate using various rules and interpolation when you need. And then you solve a Newton method. But again, I mean, obviously the limitation for this method is you cannot have a very large number of unknowns because of these restrictions in computation. So in the end, we do the same trick as for 2D stuff, and we jump from some forced branch in a non-forced branch, and this is half of the solutions we obtain in this case with no forcing. And this is very close to this minimum, so you have obviously it's truncated, force truncated here. So if you carry on, this will look like a lump. Again, we've seen yesterday on Professor Akela's talks. So this is half of the solitary wave. So again, what we're trying to do is to obtain a solution for the full problem now. Now, again, a third different problem. So this is probably the fifth one since I started my talking. And yeah, it's probably too late now to stop the messenger. So now forget the gravity. So another interesting problems, which I think is interesting, is the so-called the Kinner-Sleeve problem. So you have a fluid sheet, you have capillary on top and at the bottom, and you obtain the so-called the Kinner-Sleeve problem, because Kinner-Sleeve was the one who obtained them. And you can have like in phase, like symmetric waves, like that, or anti-symmetric. Again, my drawing is not perfect, but I've got an idea. Now, what happens if instead of considering the surface tension, this is some work done with Mark Blight and Jean-Marc, we assume that the liquid is between two elastic plates. So again, now I have no gravity, obviously, because otherwise all these things will fall down. And we try to find out if we find similar solution with Kinner-Sleeve, and the answer is yes, we can. And I'm looking for periodic solutions. As I say, I talk a little bit more about numerical method because it's a numerical day. I'm introducing again the complex potential as before, and now we introduce this sort of analytic function tau minus I theta, which is given by this relation. And then those are the equations on the plates, on the upper and the lower plate. Again, because we have no gravity, obviously the rho g term disappears. This is our friend from the previous problems. Now the curvature is not that dreadful, so this is the curvature in this sort of new variables, tau and theta. And even k double dash, kappa double dash is not that complicated. And we want to solve these two equations. So as I say, I expect to see this sort of waves like symmetrics and anti-symmetrics. And we expand tau minus I theta as a series, and again, if I have to find A and B ends. And we use the collocation method. So it's more or less the same what I said before. So you obtain again 2n equations with 10 unknowns. And that's the sort of solution we found. So this is close to whatever when they start. And this is sort of almost limiting configuration. So there is some differences, and this one is for anti-symmetric one. So what happens with kinetic solution? So the kinetic solution end up in this sort of self-intersecting profiles, as Krappel solutions do. In this case, they don't. They go to this sort of limiting profile, which corresponds to waves when you have no speed. So again, the limiting profile is more or less at c equals 0. And you can have all sorts of other things here, which I'm going to skip. So you can have bifurcation from these branches, which solutions which are not purely symmetric or antisymmetric, but they are a combination of the two. So one branch is like that, and the other is going to a straight line. So that, again, that's slightly different from the limiting cases for the capillary problem. So that's my focus of today's talk: the similarities and differences. So some conclusions before finishing. We can or we are able to generalize most of the algorithms for capillary gravity problems to compute flexural gravity problems. You see there are plenty of similarities, but there are also some differences, like limiting cases and so on. And again, the limitation, I mean, if you think, so this is perfectly fine, waves under an elastic plate. If you think of ice, again, you have to take care of this sort of strain in ice. You have to compute sort of the strain in ice and see when the strain is more than the yield strain of the ice, which at some point I need the values like 4.10 to the minus some 4 and so on. And you can easily compute this sort of strain for all the solutions to see which are more or less realistic in some sense. And as I say, sort of what I'm doing now is looking at the whole 3D model with this sort of full nonlinear terms for the plate, and ideally at some point do some stability or so on these waves. Thank you.
Questions for our speaker?
So you computed a lot of maximal waves in 2D.
Yes?
What about 3D? What's the biggest lump look like?
The one we've seen before, or those ones?
Yeah, what happens if you continue that branch to the large amplitude?
It's sort of similar with the capillary
It's an
gravity stuff.
axisymmetric bubble.
Axisymmetric in so you obtain the classical symmetry on x and y. So just it is very similar with
But
the
there's a bubble.
bubble.
The largest amplitude does
The limiting one. Oh yeah, no, I don't know, because I mean this algorithm is not cannot take care of this overturning. The 2D one can.
Oh.
Different parameters. I'm working on the inverse plane there and so on. I have x of phi, y of phi. While here, I think I've done something wrong. I say I finish my talk and automatically. Yeah, so I can't go with this parameterization anyway. I mean, we have to use this sort of overturning type formulations. But the integral, Philippe has done this sort of stuff with overturning things.
Well, imagine if you do compute till the surface is touched. It's going to be rather unexpected if they all seal up all at the same time. So you can imagine touching in the middle while being open at the end.
Yeah. I mean,
So
it's
More like symmetric, a custom
more of an
bubble.
actual system. Yeah,
Yeah.
strange construction.
Not a 2D.
Other questions? Our speaker again.